Okay, this video of this lesson is being recorded after the fact, not while we conduct class, because the one I made during class, I neglected to have the Bluetooth audio turned on. So there won't be any of the natural pauses or rhetorical questions or real questions that tend to slow down the video. So it'll go pretty fast, and if you want to slow it down, then just pause the video and hit play again when you're ready to keep watching. This lesson is about relations and functions, which are topics that you've had before. It specifically addresses the second bullet on the SOLs, although really only in two particular concepts, which are domain and range. The other concepts of zeros and intercepts will be in later lessons. Okay, a relation is a set of input and output values, which we can represent in four different ways. You can write ordered pairs, and by ordered pairs we mean X and Y values, where it's usually written in parentheses, X comma Y. The first number in parentheses represents X, the second number represents Y. It could be written as a mapping diagram, where there's one bubble for the input values, another bubble for the output values, and arrows that connect them. For example, in our ordered pairs, -3 and 4 were together. So in the mapping diagram, there's an arrow that goes from -3 to 4. A table of values is pretty much the ordered pairs, right, written in a table format. Or you could graph them as points in the coordinate plane. In the coordinate plane, again, this should be review, is a rectangular grid where the X coordinate is telling you how far you should go left or right of the middle, and the Y coordinate is telling you how much to go up and down. Right, the middle of the graph is 0, 0. So for example, the -3, 4 would be 3 to the left and 4 up, and you draw a point. And what you don't do, if you're given a set of points like this, don't try to connect the points with a line, because there is no line that connects them. It's just these points. Okay, this is from what they're calling problem 1. I'm probably going to say example 1, because that's what it really is. But it's just giving an example of a relation presented in the four different formats that we just saw. This particular relation is the input values are the time since a parachutist has jumped out of his plane and his height or altitude. And in a mapping diagram, here we see at 0 seconds since he jumped out, he's at 10,000 feet. At 4 seconds since he jumped out, he's fallen to 9,744. Right? So this is our mapping diagram. These are the ordered pairs, table of values, and graph. And notice on the graph that the shape of the graph is curved. And we will be learning in this class in Algebra 2 a whole bunch of different functions with different shapes that help us to model the particular real-world situations. In this case, we will learn about quadratic functions who have the shape of a parabola, and then we could use that to model this real-world situation. Okay, some vocabulary words. Domain and range, which are review concepts for you, but just to remind ourselves, domain is the set of all the X coordinates, the inputs, and the range is the set of all the Y coordinates, the outputs. If we go back to our parachutist problem, here's all the ordered pairs. Again, this is a set of ordered pairs, and notice the curly brackets on either side. Those are set brackets. So it means that what's inside is going to be the same thing in a list separated by commas. So here's our ordered pairs. And they've highlighted in red the X coordinates, which make up our domain. And our Y coordinates are in blue, and they make up the range. And Here's a try it yourself kind of thing, and in order to save a little time, I will just say, since the domain is being written in red, that the domain of this problem is the -3, 0, 2, 9, 23. Switch to blue for the range, 14, 7, 0, -18, -99, right? That is domain and range. Function. Function is a word that we're all familiar with, probably more so than relation, but function is a relation, but it's a particular kind of relation. It is a relation, that means a set of input and output values, where there is specifically only one output value for every input. For example, if you have a job where you're paid by the hour and you want to know how much will you get paid if you work 10 hours, you expect to get one answer. You don't expect to get, maybe you'll get $80, maybe you'll get $100. You expect one answer. In that sense, a function is a relation that works. It answers a question explicitly, clearly, right? There's not two answers, there's just one answer. So for every input, one output. Right? To identify a function, when we're looking at a finite set of points, that is a fixed number of points, in a mapping diagram, what you look for is if there's more than one arrow coming from the same member of the domain. And as you see in this one, the -3, 0, and 4, they each only have one value connected with them. So there's only one arrow leaving that element of the domain. So this is definitely a function. But when you come over to this set of ordered pairs, right, then you can see that here you got when x is 4, y is -1. But here it says when x is 4, y is 1. So for one input value, there's two output values. That's not a function, right? Not a function. Right. Again, here's another check for understanding. What would we say about this one? And again, if you want to pause here to give yourself a chance, then by all means do that. The domain, and here's the domain and the range. What are we looking for in a mapping diagram? More than one arrow from the same elements of the domain means not a function. And in this case, you've got more than one arrow coming from the number 2 in the domain. So this is not a function. Right, then we come over to the set of ordered pairs. And do you see any repeats in the x-coordinates? And the answer is no. Right, the x-coordinates, -7, 9, 14, and 7, no repeats. Therefore, function. And the one thing to notice in here is that there actually are repeats in the y's, right? That's okay. It can still be a function if it has repeated y values. That would be like saying, if I have a set price for how much it's going to, or a set cost for me to paint one room in your house, and you say, well, how much is it going to cost if it takes me one day? And I say $200, let's say. How much is it going to cost if it takes me a week? $200. It's the same output value in both cases, but it is only one output value. That's what makes it a function. Right. Unfortunately, most of the time we don't have a finite set of ordered pairs to look at to examine whether or not it's a function. We have an equation which is represented by a graph, and a graph which is made up of infinitely many points. For every value of x you plug in, you get another output value, and that's another point on the graph. And what you plug in for x can be any real number, any rational number, any irrational number, and just imagine on any, even though you're well aware that it takes 2 points to define a line where it is a straight line, there's infinitely many points on this line. In fact, if you take any little piece of this line, there's infinitely many points on it. So we'll never be able to, with something like this, or the graph, look at a set of ordered pairs and say, oh, there's repeated x values. That's not a function. So we have another method to determine whether a graph represents a function, and that is called a vertical line test. With a vertical line test, you look at your graph, and if you can imagine any place on that graph that a vertical line would cross in more than one place, then it's not a function. So this first graph, right, we have a vertical line and it's crossing once, twice. So for the same x value, there's 2 different y values. That's not a function, right? So repeated x means, I shouldn't even say repeated x. I should say more than one intersection means, therefore, not a function. Because for the same value of x, we've got more than one y value. Now, our line from the other page, I cannot imagine any vertical line could ever cross a straight line in more than one place. So that's a function. Right. What is the only straight line that would fail a vertical line test? Pause. Answer the question. And the answer is a vertical line. A vertical line fails the vertical line test because for this one x coordinate, which in this, the way it's drawn, looks like x equals 3, there's infinitely many y coordinates. Not just 2, infinitely many. So a vertical line, meaning straight up and down, is not a function. A horizontal line is actually a function. That's not a problem. Right? If I draw a horizontal line, you know, that's like me painting a room for a fixed amount of money, right? It doesn't matter if I put in x equals -1 or if I put in x equals 2, I get the same y value, but at least I only get one y value. Right, here's 3 examples given in their example 4. You could see this first, and I need to switch back to the pen. This is not a function because of 2 crossings. Not a function. Right, the next one, obviously they've drawn a vertical line and it's only crossing in one place. More than that, you have to imagine, is there any place on that graph you could imagine that vertical line crossing more than once? If you could move it side to side? No. So that's a function. The last graph is just a finite set of points, but actually 2 of those points are on the same vertical line. So that's not a function. Okay, then here's the check understanding. So if you want to pause here, pause, answer it, hit play when you're done. Letter A, again, not a function. Now, the ones that are not a function, it's easy. Just draw the line and you're done. The rest of them, I mean, you can't draw infinitely many lines. We could draw this set of vertical lines, and looks like that's a function. This graph, definitely going to pass a vertical line test. Wouldn't pass a horizontal line test, and we will get to that somewhere in your math career, but it does pass a vertical line test, so that's a function. Now, this for Algebra 2 trig specifically, a lot of times you got to tell domains and ranges from graphs, not just whether or not it's a function with a vertical line test. And it's easy maybe to look at, easier to look at number 30 first, but you could see this ellipse has an infinite number of points on it. But those points are confined on the x-axis between -3 and 3. So when you have a continuous graph like this, you have to use a range of values, which we use inequalities to represent that. That's why we studied them in the previous chapter. So the domain of this ellipse would be -3 is less than or equal to x is less than or equal to 3. Again, there's our three-part inequalities again. Range, right? The range, the y-coordinates are between -1 and 1. There's no points above 1. There's no points below -1. So -1 is less than or equal to y is less than or equal to 1. Right? This one, in some sense, a little trickier. You got to get used to looking at these things. But when you see these arrows on the end, it implies that the arrows go on forever. And it's going to the left and it's going up. Right? It's going to the right and it's going up. So side to side in the x coordinates, it's going from infinitely to the left and infinitely to the right. So we would say that is domain, all reals. And the range, the points that make up this graph don't go infinitely down. They actually stop at y equals 0. So you would say y is greater than or equal to 0. Okay. Talk for this for a few minutes. Okay. Function notation. Function notation is f parentheses x end parentheses, right? You can see down here, it's read as f of x, right? This is not a multiplication. You can't peel away the f from the x. Sometimes students will try to divide by the letter f, but it doesn't work that way. It's all together. So notice these two. The first one, y equals 3x plus 2, we should recognize as a basic linear equation, y equals mx plus b. But in the second one, instead of a y, you have f of x, because the y and f of x are interchangeable. It's the same thing. Right. So because it's solved for y, in order to know what y is, you plug in a value for x, and you say, well, what value are you going to plug in? Anything you want. X is the input value. You get to choose. It's also called, x is the independent variable. It's independent because you get to choose it. Right. Y, the value of y depends on what you plug in for x, so it's called the dependent variable. And I should put in variable. I mean, just like we, in the first chapter, evaluated an expression by plugging in a value for the variable, you can evaluate a function by plugging in a value for x, which is a variable. So in this third representation where it says f of 1, that means in place of the x in 3x plus 2, put a 1. So f of 1 is 3 times 1 plus 2, which is 5. So here's this, that is a point on a graph. When x is 1, y is 5. Right. If I can graph this graph, y equals 3x plus 2, by making a table of values. And the point of this exercise is just to tell you, at the beginning of every chapter, we're studying a new kind of function, and we will probably be making a table of values in order to understand the shape of the graph. And there's always the question, well, where do I get these x values? And if you remember on the last slide, we said x is the independent value, the variable you choose. So I'm going to pick x equals 0 and x equals 2, right? Because you get to choose those, I get to choose those. You know, seeing the grid that I've set up to graph, I think 0 and 2 will probably be pretty good. They're right in the middle of my graph. So, you know, plug in values of x that make it convenient for you. So in the second column, f of x equals 3x plus 2, you know, that's the f of x or y, also known in this book as the function rule. You can plug in 3 times 0 plus 2, which is 2. And 3 times 2 plus 2, which is 8. So that gives us 2 points to plot, 0, 2, and 2, 8. So let me plot those points, 0, 2, and 2, 8. And that, most of the time, we'll probably have to plot more points than that because we don't know the shape. But we know the shape of a straight line. Right? If we know it's a straight line, we need 2 points. So that's all we're going to plot. There's our graph. So the main takeaway from the slide is when you make the table of values, you get to choose the x values. Okay, evaluating functions. Right? F of x equals negative 4x plus 2. What is the output for the given input? Okay, which means if in this first one, if the input is negative 2, that means we're finding f of negative 2. And f of negative 2 would be negative 4 times negative 2 plus 1, right? I'm just taking this and putting it in there, which is 9. Try this one. F of 0 equals negative 4 times 0 plus 1, which is 1. What is f of 5? Negative 4 times 5 plus 1, which is negative 19. Right, those are 3 points on a graph. Right, this is negative 2, 9. This one is telling us 0, 1, which is, by the way, the y-intercept, because when x is 0, you're right in the middle of the graph. You're not to the left, you're not to the right, you're right on the y-axis. The y-intercept is 1. And here is 5, negative 19. Okay, there will be a word problem in homework, which is somewhat similar to this. This is the you try, check for understanding underneath what they call problem 6. It says you are buying bottles of a sports drink for a softball team. Each bottle cost $1.19. What function rule models the total cost of the purchase? And evaluate the function for 15 bottles. Now, my guess is that if you were given that question on a test, you would get it right almost every time without anything that we're learning in this lesson today. However, we're going to go through the process here of defining a function rule. First, we should define what our variables are. Okay. What is it that we're trying to model? And we are modeling total cost. So we should come up with a variable that represents total cost. That's actually not just a variable, that's our function. And how about we'll say C for cost. So C is going to equal some expression that represents the total cost. What does our total cost depend on? And it's going to depend on how many bottles that you buy, right? The more bottles you buy, the more your total cost. So we need a variable that represents that. Right? C is total cost. B is the number of bottles. So our function C is actually a function of how many bottles. So instead of f of x, we're saying C of B. And what will be the expression that represents how much it costs as a function of the bottles? Well, it costs $1.19 per bottle. So we would say it's $1.19 times the number of bottles. That's your function rule. And then how would we evaluate the function for 15 bottles? That means plug in 15 for B. And we'll get $1.19 times 15, which equals, let me see if my calculator's still going here. Clear. 119 times 15, 1785. Okay, that's the lesson, right? Again, this is a review lesson. We reviewed relations and how you identify functions, which should be things that you've learned before. We actually reviewed domain and range, at least to the extent that you learned it before. But this will get more complicated. So it is part of the SOL for Algebra 2. The rest of those things we'll worry about later. And that was the homework.